All right, guys, here we are back again to finish up our last topic in stoichiometry, limiting reactants. Now, so far, we've just sort of looked at limiting reactants more conceptually. I mean, we did the mole ratio lab with the calcium nitrate and sodium oxalate. And in that lab, what I hope you guys got out of that lab was you notice that when the mole ratio in the amount of products that you actually add is different than the mole ratio in the balanced equation, then there is an imbalance in those amounts, and the amount of product that would be made can suffer. The amount would not be as much when the amounts of reactant are not in the proportions that are designated by the balanced equation. Likewise, we saw with the magnesium and hydrochloric acid demonstration, a very similar thing. When the proportion of magnesium to HCl was not in the 1:2 ratio given by the balanced equation, the amount of hydrogen gas that we made was not enough, was not as much as we thought we would. So really all that's left is for you guys to actually solve some limiting reactant stoichiometry problems. And so what you might be wondering right now is, well, yeah, we saw the mole ratio lab, we saw the HCl and magnesium demonstration, but how does that translate into solving a problem using stoichiometry when there is a limiting reactant? And so the first thing we want to look at, and I have an example here, the reaction of calcium with silver 1 nitrate to produce silver and calcium nitrate. I want to look at, first of all, how does a limiting reactant problem present itself to you? How does it look different? How would you be able to recognize a limiting reactant stoich versus the plain old garden variety stoich that we've done up till now? So that's what I'd like to go over. Then I'll go through the problem solving process, the steps in the problem solving process, and then finally I'll go over 3 examples of how to solve a limiting reactant problem. And then it's all over but the worksheet. All right, well, let's first see how a limiting reactant stoichiometry problem presents itself to us. So how many grams of silver will react, would be made, I'm sorry, if 20 grams of calcium reacts with 100 grams of silver 1 nitrate. And so we see that silver is going to be our substance B. That's the substance that we want to calculate. But wait, over here on the reactant side, we have 20 grams of calcium, so that would be my A. Wait a minute, wait a minute. We also have a given amount for silver nitrate, 100 grams of silver 1 nitrate. So that could be my A. Oh, now you see the difference in a limiting reactant type problem. We really don't know which one of these guys, which A we should use to calculate the amount of silver we would make here. Well, if you think back to the definition of a limiting reactant, we use the limiting reactant in stoichiometry. If you think back to our definitions, the lecture where I gave the definitions, you're going to use the limiting reactant to calculate the amount of product because, of course, like in the S-burger recipe thing, the limiting reactant is what determines the amount of product. So I guess that what that means is we first have to figure out which one of these 2 values would be limiting, and once we do, then we'll use that as our A to calculate substance B, the amount of silver. Okay, so actually let's go through the problem solving strategy as we did with regular stoichiometry. Now, I know you're looking at this and you're saying, oh man, that's a lot of words there, Mr. S. Well, actually the blue part, the stuff that's in blue, is the same as we learned before. The only thing that's going to be different about a limiting reactant problem is going to be this step here. And that's in green. So anything that you see in green will be unique to a limiting reactant style problem. So of course you have to balance the equation. In step 2, determine which participants are the given substance. And that's what we saw was different in the example above with calcium and silver 1 nitrate. Instead of giving you 1 starting amount, I gave you 2 starting amounts, both on the reactant side. Well, we still have to diagnose the type of stoichiometry problem. And both A's that were given above were in grams. Our desired unit was grams. So no matter what, no matter which A ends up being the limiting reactant, this is going to be a mass of A, whichever one of those two A's it is, to mass of B. Stoichiometry problem. Okay, step 4. Well, as we said, the limiting reactant is the substance, whatever the limiting reactant is going to be the substance that determines the amount of B that's made. So how do you determine which given amount of A would be limiting, would be the limiting reactant? Well, here's how we're going to do it. Now there is a number of ways. There's probably 4 or 5 different strategies for for figuring out which reactant is limiting. And the one I'm going to show you, I think, is the one that's pretty much the simplest. Okay, not a lot of bells and whistles here. We're going to be doing things that we are used to doing, like calculating number of moles and using the mole ratio. So the strategy that I've chosen of the numerous strategies to solve limiting reactant problems is the one I think that uses tasks that we've already learned before over and over again. So hopefully you'll find this not too difficult. So again, the first way you're going to determine which given amount of A would be limiting is first you're going to calculate the moles of both A's. So instead of calculating the moles of just calcium, you're going to calculate the moles of calcium and silver 1 nitrate in this example. Okay. Then what you're going to do is you're going to multiply both of those mole numbers by the mole ratio to find the moles of B. And really what you're going to do is whichever one of those two amounts of A results in the least number of moles of B, right? If you make the least amount of B, well, then you're going to be the limiting reactant. So then that A would be the limiting reactant, whichever substance A results in the making of the least moles of B, the least amount of your product in moles, that's going to be the limiting reactant. And then really what we have to do to get mass of B in this case is take that moles of B and then use the molar mass of B to get the mass of B. So once we determine which A is going to be our limiting reactant by determining which substance would make the least number of moles of B, we just convert those moles of B that would be made by the limiting reactant to the desired units for B, and again, in this case, mass of B. So really the first 3 steps are the same. You're still going to balance your equation. You're going to set up your problem. What's your A? In this case, what's your A's, plural, and what's your B? You're still going to want to know what units I give you for A and note what units are desired for B. So the only thing different is going to be this middle part, and the ending part is going to end the same way as any stoichiometry problem. So let's go over 3 different sample problems to kind of illustrate this problem-solving process, how you would execute this problem-solving process in a real stoichiometry problem. Okay, so our first sample problem will be the problem that I started us off with. How many grams of silver would be made if 20 grams of calcium react with 100 grams of silver 1 nitrate? And again, in the setup, this is B. I want to know how many grams. Here are my 2 possible A's. And the first step in the step 4A says, calculate the number of moles of each A, substance A. And so I'm going to start off with a mole conversion, and then ultimately I'll multiply that by the mole ratio. So that's why I made these lines a little extra long. But let's go ahead and do the math that would calculate the number of moles of calcium and the number of moles of silver 1 nitrate. Okay, so here we are. So calcium's molar mass is 40.078 grams per 1 mole. And so to get moles, I would divide by the molar mass. Molar mass of silver 1 nitrate, since I want to calculate moles, 169.873. So again, 100 grams divided by the molar mass of silver 1 nitrate per 1 mole. And if I actually stopped right here, and I actually did the math for these, I would have how many moles of each A. But what I'm going to go ahead and do now, before I would even do that math, step 4B from the previous page says multiply each one of these mole numbers. This would be moles of calcium if you look at the units that are left, and this would be moles of silver 1 nitrate. If you look at the units that would be left. So instead of actually doing the math and writing that number down, I could just go ahead and tack on step 4b, which says multiply each one of these by the mole ratio from the balanced equation of the coefficient of B over the coefficient of A. Okay, so for calcium, the mole ratio would be 2 from the balanced equation, 2 moles of silver for every 1 mole of calcium. And remember, again, the mole ratio is B's coefficient over A's coefficient. For silver nitrate, the mole ratio would be 2 moles of silver for every 2 moles of silver 1 nitrate. You see, again, B's coefficient over A's coefficient. And then what we're going to do is we're going to actually find the numerical value here. And whichever one of those is the least amount of moles of B is going to be the limiting reactant. And that is the amount of moles we'll use to do the final step, which is to get the grams of silver. So when I do the math, I see that if I assumed that calcium was the correct A, I would make 0.998 moles of silver. If I sort of assume that silver nitrate is the A, silver nitrate is the limiting reactant, I would make 0.589 moles of silver. And this is the amount of moles of silver that is the least. That means that silver 1 nitrate is the limiting reactant. By definition, if you think about our S-burger recipe lecture, calcium then would be the excess reactant. You have too much calcium, and the way you know is because using the amount of calcium as your A, you think you're going to make more silver than you actually can. So again, with silver 1 nitrate as our limiting reactant, we're going to do the final step. So let me set that up now. So now that I have moles of B, if I want to find the mass of B, I multiply by the molar mass. Okay, just like you would normally have done in the stoichiometry problem after the mole ratio, right? Step 5 on the previous page says go ahead and multiply by whatever factor, either the molar mass or Avogadro or mass of B divided by the density, whatever you need to do to get these units for substance B. And to go from moles of silver to mass of silver, I'm going to multiply by the molar mass. And when I do that, I get 63.5 grams of silver. This, my friends, is the final answer. So the answer to how many grams of silver would be made if these two amounts reacted, well, because silver 1 nitrate is the limiting reactant, we would only be able to make 63.5 grams of silver. That's the final answer. All right, let's look at a second sample problem here. Okay, different equation. Iron plus oxygen makes iron 3 oxide. And I balanced it. So what I want to know is how many particles, so Fe2O3, iron 3 oxide is our B, would be made if 160 grams of iron reacts with 100 grams of oxygen. And again, I write, just like I would do any stoichiometry problem, I write down the given amounts, but I don't know which one of these will be substance A. Again, whichever one of these is the limiting reactant is the one that I'm going to use to calculate the number of particles of B. Let's do that math now. And again, the first step in a limiting reactant problem would be to turn these numbers into moles. So again, I'm getting ready to do my mole calculations. Again, notice how I set this up. I'm modeling for you guys a good way to do this. I just kind of separate it by my two possible substance A's. I'm going to do my iron calculation here, moles, convert to moles, and then multiply by the mole ratio, convert to moles of oxygen, and then multiply by the mole ratio. And that way I can easily see which one of these is the least number to go on with my limiting reactant stoich. So here we go. Calculate our moles. Okay, molar mass of iron, 55.845. That will get me moles of iron. Molar mass of oxygen is 31.998 grams for every 1 mole. And now what I'm going to do is I'm going to fill in the mole ratio. For iron, it's going to be 2 moles of Fe2O3 for every 4 moles of iron. In the oxygen setup, it's going to be 2 moles of Fe2O3 for every 3 moles of oxygen. Okay, so I've written it in. There's my coefficient of B over my coefficient of A, coefficient of B over coefficient of A for oxygen. Okay, let's do the math. So 160 divided by 55.845 times 2 divided by 4, right? Anything in the denominator you're dividing by. That'll give us those moles. That was 1.43 moles of iron. For oxygen, 100 divided by 31.998 times 2 divided by 3, and I get 2.08 moles of oxygen. So which one of these guys would be, I'm sorry, not moles of oxygen. I'm sorry, I did those incorrectly. Pardon. Sorry, guys, I actually put the wrong units there, so I apologize. Let's see, what are the correct units? Well, I'm sorry, if you look at the green that I just crossed out, it would be 1.43 moles of our product. Duh. Fe2O3, and it would be 2.08 moles of Fe2O3. Sorry about that, guys. So correct that in your notes. Now, let's look at what our limiting reactant is. Our limiting reactant would be iron, because using the amount of iron to calculate the moles of B, we find that the iron amount would give us the lesser amount of product. And so that is going to be our limiting reactant. That means that oxygen would be too much. So the 100 grams of oxygen is actually too much oxygen for the 160 of iron. That's okay. And then what we're going to do is we want to calculate particles. And so we're going to use Avogadro, right, to convert the 1.43 moles of product of Fe2O3 into particles. There you go. I apply my Avogadro's number. Do the math, and that would be my final answer. Now you may be wondering what's going on with this here. Well, this is a dead end. Okay, this amount here is how much would be made using my excess reactant amount, and that's irrelevant. Think back to the S-burger recipe. If we would have used the excess ingredient, we would have thought we could have made more S-burgers than we really could. And so at this point, once you decide what the excess reactant is, well, that guy becomes like a non-entity. And in fact, this is definitely not your A, because this is the limiting reactant. It is your A. The question mark goes away. That is your A. And if you kind of see, that's really what I did. I used this amount, the amount that is of my limiting reactant, to calculate my particles of B. All right, let's do one more example. We'll go through this one a little quicker because we've already seen several of these. So I'll do most of the writing out, and then I will actually then just kind of go through my setup. Okay, here's my setup. I have my two A's. I have my B, because that's what I say, how many liters? Oh, in this case, I want liters. And so I'm actually going to want to find volume of B. And because I give you the density, this is going to be volume of B using density. So that would be like a mass of A to mass of B divide by the density. Okay. But first, before I do that, I have to figure out which one of these two, carbon monoxide or iron 3 oxide, is my limiting reactant. So here's my first setup. This will get me moles, and then I'm going to tack on the mole ratio. Okay, so there's my mole ratio for carbon monoxide. The mole ratio would be 3 moles of CO2 for every 3 moles of CO. When I look at the iron 3 oxide setup, it's going to be 3 moles of carbon dioxide for every 1 mole. Do the math, and we get in this problem, using the amount of carbon monoxide, we think we would make 2.16 moles of B. Using iron 3 oxide, we'd only make 1.88 moles. Therefore, ding, 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 Fe2O3 is our limiting reactant. So this is our A. This amount is now the excess. This represents the excess reactant. And this amount of the 60.5 was actually too much of carbon monoxide for this 100 grams. So it would, some of that 60.5 grams would be excess. Again, though, what we're going to do is we're going to use our limiting reactant, Fe2O3, to carry our problem on. So we need to go from moles of B, we need to go to mass of B, and then divide by the density. All right, so we take our limiting reactant at where we're at the moles of B step. To get mass of carbon dioxide, we multiply by the molar mass, 44.009 grams per 1 mole. And then we divide by the density in order to get liters. And if you complete the math, we would find that using, in this problem, if we took 60.5 grams of carbon monoxide, reacted that with 100 grams of iron 3 oxide, which now we know is our limiting reactant, we would make 50.4 liters of carbon dioxide. All right, guys, so that's pretty much it for these notes. And you'll have a worksheet that I would just, the way you would do it is just kind of go through the problem solving process that I've modeled for you here. Actually, on the worksheet, the very first problem, I've gone through and go ahead and worked it out for you. So actually on the worksheet, you'll have another example similar to one like this. And then just go ahead and finish up those. And again, if you have any questions, that's what the daily Zoom Q&A sessions are for. So take care, guys. This is pretty much it for stoichiometry.
That was easy. That was easy.
I sure hope so. Take it easy, guys.